Hello? Okay, great. All right, well, welcome back, everybody. So now that we've gone through a tour of one-dimensional and two-dimensional topological superconductors, I want to turn to maybe the most exciting manifestation of all of this, which is the phenomenon of non-abelian statistics. So we've seen so far that in one-dimensional topological, in the Kitaev chain example, if you have a domain wall between a trivial phase like vacuum and a topological superconducting phase, there's a Majorana zero mode bound to that domain wall defect. And in the context of 2D, if you have a vortex in a two-dimensional topological superconductor with its corresponding branch cut, that also binds an unpaired Majorana zero mode. And by virtue of those Majorana zero modes bound to those domain wall or vortex defects, those defects behave like non-abelian anyons that one finds in the, let's say, non-abelian fractional quantum Hall states. Yeah? Thank you. Okay.
Can you repeat the argument about the Majorana and the vortex?
Say that again?
Can you repeat the argument on why the Majorana lives inside this vortex?
You mean from the previous lecture? Yeah, so the idea is that is a question specifically about why a vortex is kind of like a hole with h over 2e flux?
No, rather why
even for the holes. Yeah. Okay, so the idea is if you have a hole drilled inside of a two-dimensional topological superconductor, there's a chiral Majorana edge state that has to intervene between those two phases, the vacuum and the topological superconductor. And if you have a flux quantum, h over 2e flux quantum, passing through that hole, then there's an Aharonov-Bohm phase of -1 that unpaired fermions acquire as they go around that. Okay, so you have fermions that are encircling that h over 2e flux in the form of that chiral edge state, and correspondingly their boundary conditions get toggled by the presence of an h over 2e flux. And so if you started with anti-periodic boundary conditions, which we declared had to be the case in the absence of fluxes, you toggled that from anti-periodic to periodic by threading an h over 2e flux quantum, and that shifts the level spectrum for that edge state such that you have a single k equals 0 level, and that k equals 0 level has a property that gamma of k equals 0 is equal to gamma of k equals 0 dagger, and correspondingly it satisfies the same Majorana algebra that we had, let's say, these guys satisfying.
It's a literal hole with literal flux, right?
Yes, but...
Is that different from like what people expect to see in the iron telluride or iron selenium telluride?
It's different in a non-universal sense. So, I like to think about h over 2 vortices induced by magnetic field, by an external magnetic field, as a kind of self-generated hole residing in the superconductor. And if you want, you can, maybe to make that connection even more precise, you can imagine filling what I had as a hole with, let's say, some kind of normal metal, and then now it starts to look more like an actual superconducting vortex that you would have, where the core is basically some small normal pocket sitting within a superconducting realm. Okay, sure. All right, so actually one bit of nomenclature which I can perhaps comment on. I think there's often some confusion about, Majorana fermion versus non-abelian enyon. So these things so I would say the Majorana zero mode, I would never call that a non-abelian enyon. And it doesn't really matter. This is just semantics ultimately. What I would call the non-abelian enyon-like object are these defects. So in Adam's talk, he was introducing these Ising non-abelian enyons labeled by sigma. So I would say that it's this defect, which is your sigma, and the vortex defect in the 2D case, which is your non-abelian enyon. And the non-abelian enyon character that defect exhibit can be traced back to the existence of a Majorana zero mode that's bound to the presence of that's bound to that defect. Right? So calling a Majorana zero mode a non-abelian enneon to me is sort of like calling an engine a car. Obviously, like you need the engine to give the car its life, and similarly, these non-abelian defects, these sigma particles, need the Majorana zero mode to have their interesting integrity. All right, so either these domain walls or these vortices obey non-abelian statistics when you swap them around one another. And so let's try to understand how this can happen. So this remarkable property actually follows from just considering what happens when you have a pair of Majorana zero modes bound to either a domain wall or a vortex defect. It doesn't really matter. So let's start there. So let's suppose you have two defects, one binding a Majorana zero mode gamma 1, the other giving a Majorana zero mode gamma 2. So we can conveniently label the Hilbert space, the degenerate Hilbert space, spanned by those Majorana zero modes by superimposing them into a fermion operator D, like we did last time. D is just 1/2 gamma 1 plus I gamma 2. And if you look at the corresponding occupation number, D dagger D, that's just 1/2 times 1 plus I gamma 1 gamma 2. And I'll just remind you that the occupation number 0 and 1 for this D fermion corresponds to states where I gamma 1 gamma 2 are either plus or minus 1. All right, so recall that if you just have a pair of these Majorana zero modes, you have two ground states, one which has total even number of electrons, the other one which has total odd number of electrons in the many particle wave function. So with that in mind, I now want to ask, what happens if we imagine adiabatically swapping the positions of gamma 1 and gamma 2. So one thing I'd like us to all agree on is that there's no chance that you will make your way from the even fermion parity state to the odd fermion parity ground state. If all you're doing, you have some isolated superconductor, there's no way that you can find another fermion just by adiabatically manipulating the positions of these zero modes. And that's actually very important and strongly constrains what can possibly happen under this adiabatic swap. Okay, so
do you need this label of the parity eigenvalue? So does it in general only work in systems where you have this symmetry?
Well, yes, but all electronic systems have that property. It's unavoidable. It's constrained by locality.
Inversion is just it's just for these two operators, kind of like.
Yeah. Okay. So I think I understand what you're saying. So so the thing that's guaranteed by by basic fundamental properties of nature is that locality dictates that any physical system of fermions has a conserved fermion parity to it. Okay. And so the follow-up statement that I want to add to that is, we have two ground states that are separated energetically from all excited states. If we just remain in that low energy sector by performing some adiabatic operation, we have no chance of migrating from one state to the other by virtue of fermion parity conservation. Okay, so this is actually important. So, another thing that we can hopefully agree on is that when I perform this swap, gamma 1 and gamma 2, they should swap labels. Right? And the most naive thing that you might try is to say that after you completed that swap, gamma 1 goes to gamma 2, and gamma 2 goes to gamma 1. Okay, so that certainly seems to have the right spatial properties, at least, for what happens to those operators. But this can't possibly be correct. The reason it can't possibly be correct is that if you enact that transformation on this occupation number, if you simply swap gamma 1 and gamma 2 here, it's an I. So this goes from I gamma 1 gamma 2 to I gamma 2 gamma 1. You can anti-commute those back, and you would find that that if you started in, let's say, the occupation number 0 state for D dagger D, you would have flipped to the occupation number 1 state. But again, that's breaking sacred laws of nature. Okay. So this can't quite be right, but we can fix this by appending a minus sign either to this upper transformation or lower transformation. I will somewhat arbitrarily choose to do this for the bottom line. And so gamma 1 going to gamma 2 going to minus gamma 1. So that has all the right properties. So it's swapping the position, it's swapping the operators, but it's also, that minus sign has the crucial effect that I gamma 1 gamma 2, which is tied to the, which ground state you're in, remains invariant. Okay. So this is all important. Now that's, I'm arguing this based on inevitability, preventing violation of global fermion parity constraints. But you can actually get some intuition for where that minus sign comes from, at least in the situation where these are vortices in a 2D topological superconductor. So for that case, we have these branch cuts which emanate off to the sample boundary. And if you were to swap along the path that I've shown here, so you can see that gamma 2, en route to taking gamma 1's position, is going to cross the branch cut that emanates from gamma 1. But gamma 1 is not going to cross the branch cut emanating from gamma 2. Okay, so one of those gets a minus sign, but not the other. This is, you'll also get this minus sign incidentally if you swap domain walls in a network of two-dimensional topological superconductors, although I think it's a bit more challenging. There's not a simple pictorial illustration of that. Okay, so next thing I want to do is figure out how to enact that transformation with some unitary operator. And the idea is that that unitary operator will tell us how ground states transform under adiabatic exchanges of these non-abelian defects. I think the best way to proceed is to simply let me write something down, and then we can check to make sure that it indeed does what I claim it does. All right, so such a transformation, I claim, is implemented by a unitary operator that I'll call U12. So the indices are just telling us that we've swapped Majorana modes labeled by 1 and 2. And this has the form e to the I pi over 4 times I gamma 1 gamma 2. And to work with this, it's useful to remember that I gamma 1 gamma 2 is either plus or minus 1. That's like a sigma z polymatrix. And we can alternatively write this as cosine pi over 4 plus I gamma 1 gamma 2 times I sine pi over 4. Okay, and you can just check if I gamma 1 gamma 2 is plus 1, then this should be e to the I pi over 4, which indeed it will be from the second line. And if I gamma 1 gamma 2 are minus 1, you should get e to the minus I pi over 4, which again you do. Okay, so let's check that this is the right operator, that when we conjugate gamma 1 and gamma 2 with this operator, we get the transformations on the right side. Yeah?
Does it matter that it's outside?
Well, okay, so this situation that I'm imagining would not be possible, as far as I know, if you had two Majorana zero modes, one which was at a vortex core and the other which was delocalized along the boundary. I don't know how to swap those things. So I'm really imagining a situation where you have no Majorana zero modes at the outer boundary, and you just have, at least in the 2D case, you just have two Majorana zero modes that are in the interior of your sample, bound to vortices, which I imagine in principle being able to drag around each other.
Yeah, but if you say have three of them, right, then you will have additional one.
Impossible. Oh, well, no. Oh, that's my setup. This is just the. We'll go to more vortices shortly, but all I have is two for now. Okay, so let's check. So let's start by conjugating gamma 1 by U12. So I think the most efficient way to do this is to observe that if I take gamma 1 past U12 dagger, it's actually going to, so gamma 1 anti-commutes with I gamma 1 gamma 2, and so it's just going to change the overall sign in front of here. And so that'll have, if I take gamma 1 past U12 dagger, I'm going to remove the dagger. Okay? So this is equal to U12 squared times gamma 1. And this is a nicer way to do this, to represent this operation, because U12 squared, that's actually just I times I gamma 1 gamma 2, because this becomes a pi over 2 instead of a pi over 4. And then that's what you get. Okay, so this U12 squared will just give us a factor of I times I gamma 1, gamma 2, and then I have a gamma 1 left over. So I want to now anti-commute gamma 2 past the gamma 1, so that'll give me a minus sign. That minus sign will actually cancel with the minus sign from the I squared. Remembering that the gamma 1's just square to 1, this will just give me gamma 2. Okay, so let's do the same thing for this second line here. So if I look at U12, gamma 2, U12 dagger. Similarly, I can play the same trick, move gamma 2 to the right. This just becomes U12 squared gamma 2. It's the same as here. I just replace gamma 1 by gamma 2. So I get I gamma 1, gamma 2 times gamma 2. So this one's even easier. So the gamma 2's just give identity. I squareds give us a minus 1. And this is just minus gamma 1. Okay, so you get that sacred minus sign as required. All right, so now I'd like to generalize what we've done here to a situation in which we have many domain walls and or many vortices. So let's suppose that instead of just having 2 of these, I have some even number p of Majorana zero modes. Gamma 1, gamma 2, gamma 3, and so on to gamma p. And I'm going to assume that all of these Majorana zero modes, if we're in the 2D case, are residing in the interior of our sample, which requires that p is an even integer. Okay, so now instead of having just 2 ground states as I had here, which I wasn't actually able to go between because of fermion parity constraint, now I'm going to have more ground states when p is larger than 2. And so the way to do the bookkeeping is you can take each pair of Majorana zero modes, you can assemble them into a fermionic operator, as we did here, that has a 0 or 1 occupation number. So for instance, these 2 could define a fermion gamma 1 plus I gamma 2. The next pair could define another fermion gamma 3 plus I gamma 4, and so on. Each pair will give us a 2-level system, which can be filled or empty without changing the system's energy. And in general, if we have p of these Majorana zero modes, that'll give us a ground state degeneracy consisting of 2 to the p over 2 states that are locally indistinguishable from each other. Okay, so now half of those states will have overall even electron number, and the other half will have overall odd electron number. And so now, fermion parity constraints no longer so sharply suppress the possibilities of what this kind of braid can actually do. And as we'll see shortly, if you now perform swaps among these Majorana zero mode operators, that's going to have the effect of rotating you within this ground state manifold. Okay, and that rotation is essentially the essence of non-Abelian statistics. And to get some more intuition, I probably should have said this before, but what we're really doing when we swap Majorana zero modes, we're swapping in some sense, well, maybe it's better to mention that in this picture. So I have a bunch of these superposed gamma 1 plus I gamma 2, gamma 3 plus I gamma 4 operators, and so on. And when we swap pairs of Majorana zero modes, in some sense we're taking half of a fermion and swapping it with half of another fermion, and that kind of naturally will wreak havoc on the quantum state that you're starting from, in the sense of non-trivially rotating your system within this ground state manifold. All right, so fortunately we've done already all the hard work to establishing that something like this indeed happens. So we can straightforwardly generalize what we did here to derive this U12 operator to obtain an operator that swaps arbitrary nearest neighbor pairs in this array.
One question.
Yes?
How would you break the domain wall defects? And how would you break domain wall defects?
Domain wall defects. So yeah, so that so the idea there is that if you are in a strict 1D, you can't, right? They inevitably collide. But if you imagine that you can move out of one-dimensionality by, let's say, patterning these Kitaev chains on some kind of two-dimensional grid, then you have actually enough freedom to move positions of Majorana zero modes without them coming into contact. And in that sense, it looks almost indistinguishable from what you do in the case of vortices. Yeah, so the key is just to move away from strict one-dimensionality in whatever way you like.
So this operator, so like the U operator that goes from 1 to T, is this, so I can exchange any of these Majorana modes or only like neighboring sites?
Yeah, so I'm going to view this as all I'm going to write down is an operator that swaps nearest neighbor pairs. But from nearest neighbor swaps, you can construct operators that swap arbitrary pairs of these in the array. Okay, so in a completely straightforward generalization of what we did for this 2 Majorana zero mode problem, I'll define an operator uj j plus 1, which is e to the I pi over 4 I gamma j plus 1. That swaps gamma j with gamma j plus 1. Okay, and if you swap gamma j with gamma j plus 1, then if you start from some arbitrary initial state, which is in your ground state manifold, then that state will undergo a change that's specified by that operator. Okay, so in particular, some arbitrary initial ground state will go to uj j plus 1, acting on that arbitrary initial ground state. All right, so this is really the, well, we're almost at, yeah, sorry, go ahead. Yeah.
All the different possible combinations.
Yeah.
How do you know you're not in that class?
You don't, so I'm very happy you asked this question. So it was completely arbitrary for me to choose to, let's say, superimpose gamma 1 plus I gamma 2 and so on. And actually, I can say another thing to connect to Adam's more formal lecture on this stuff. So, you know, I might, let's say, choose the basis where I label my states with gamma 1 plus I gamma 2, gamma 3 plus I gamma 4. You might choose a different, you might say, well, maybe it's more natural for me to use gamma 1 plus I gamma 3, gamma 2 plus I gamma 4, and so on. Your basis is not necessarily any better than mine, and the F symbols that he introduced are the things which allow us to communicate and relate our bases to one another. So you might say that, you know, maybe a natural basis to use is one that's inspired by the particular initialization protocol that I use, so that, you know, my initial state is expressed in some very simple way in terms of the set of fermion operators that I define from pairing up these guys. And that depends on what you did to generate these in the first place. All right, so let's reflect on this equation here. So this is telling us something that's quite extraordinary, I think. If these were bosons or bosons or fermions, you know, we know that the initial wave function would just go to plus or minus the initial wave function. If we went more exotic, if we went to the case of abelian anyons that you find in, let's say, Laughlin states, then this would be a complex phase factor that, you know, e to the I pi over 3 or something like that, which is, you know, amazing on its own. But this is even more amazing because this is not even, I mean, this is an operator. This is you know, think about this as a matrix rather than just a number. And since that you're acting a non-trivial operator on this initial state, in general, that wave function is not going to be the same as the one that you started with. Okay? And that's why I say that in general, this rotation, this exchange actually induces non-trivial rotation within your space of ground states. That rotation still has to satisfy global fermion parity constraints. If this has even fermion parity, this had better also have even fermion parity. But up to that, you have freedom to rotate, provided you have at least two states with the same global fermion parity. Okay, so this doesn't necessarily imply non-abelian statistics because maybe these operators somehow commute with each other, but indeed that's not the case. So the final step, I guess, is just to show that this is non-abelian. In other words, the order of braids that you do makes a difference in terms of the final state you end up in. And that's why we call this non-abelian. And to see that, we can observe that many of these operators commute with each other. So for instance, if I commute U12 with U34, that's going to be 0 because they have no Majorana operators in common. However, if you commute two of these operators that have one Majorana in common, so kind of nearest neighbor pair, operators that swap nearest neighbor, sorry, it's a little bit tricky to describe. So, an operator that, let's say, swaps these two versus these two, those have one Majorana in common, and as a result of that, they will not commute. Okay, so if you look at uj minus 1 uj, commuted with uj j plus 1, that's non-zero. And because of this, the braiding is inherently non-abelian. Okay, so again, if you are interested in performing some sequence of braids amongst your p Majorana zero modes, the final state that you end up in is going to be influenced by the sequence in which those individual braids were carried out. All right, so I think that's quite amazing on its own. It's the most exotic kind of exchange statistics that nature allows us to find as a matter of principle, but it's also potentially useful for something, in particular for defining operations on topological qubits. So I've already motivated that the ground states spanned by Majorana zero modes are an appealing place to encode quantum information. That was so far based on the resilience of those states, of the degeneracy to arbitrary local perturbations of the corresponding corollary that you can't detect which state you're in via local measurements. But now there's an added bonus that we can get by virtue of this phenomenon of non-abelian statistics, and that's that we'll have access to a certain set of inherently fault-tolerant gates that we can enact on qubits encoded in space spanned by Majorana zero modes. All right, so let's explore that in a little bit more detail. All right, so I'm going to phrase this entire discussion in the context of just a single elementary topological qubit. Now, if you want to have a single topological qubit that's that has 0 and 1 states that can be superimposed, you have to have at a minimum 4 Majorana zero modes. Okay, so 2 Majorana zero modes will give you a twofold ground state degeneracy, but it's useless because if you have just a fixed overall global fermion parity, you're constrained to either one state or the other, and you can't ever superimpose them. But by adding an extra pair of Majorana zero modes, we can escape that constraint. All right, so let's take a quartet of these Majorana zero modes. gamma 1, gamma 2, gamma 3, gamma 4. I'm going to, again, arbitrarily choose a basis where I superpose gamma 1 plus I gamma 2 and gamma 3 plus I gamma 4 to define two fermions that I'll use to label my states. Yeah?
I have a question with the U operator.
Uh-huh.
So is it possible to define something like a Young-Baxter equation for this U operator? Because also here we are trying to swap like two particles to.
Yeah, I mean, yeah, so these, this is not exactly my forte, but I believe that it's essential that these Yang-Baxter equations are satisfied, and one can show that this will be the case.
What are the functions for?
It's something on integrability when you want to. It's kind of a condition that you want to also see this operator that changes to particles. And the fact that you want to decompose, you can decompose a scattering in a two-particle scattering. This equation is kind of a condition that you have to this operator or something like this. I mean, I'm not an expert at this field, but just because, you know, it was something similar, and also this operator is similar to this. Something to 3 to the I something. So that's why I was thinking maybe there was some similarity with this. But yeah, there was that.
Okay. All right, so this is going to be, I'm going to define two fermion operators, which I'll call D12 and D34, that just superpose this pair and this pair. So we can catalog the states that we have available to us. In terms of those occupation numbers, and I'll divide them into even parity states and odd parity states. Okay, so in the even parity sector, we can have a state where the occupation number for both of those is 0. So let me label those occupation numbers 0, 1, 2 for that fermion, and 0, 3, 4 for this fermion. And we similarly have a second even parity state where both of those occupation numbers have been flipped to 1. And since I've flipped both, I've remained in the same fermion parity sector. And then we have the odd parity sector. Where corresponding to 0, 1 or 1, 0. Okay, so I'll somewhat arbitrarily, well, completely arbitrarily declare that we have an even number of electrons in our system so that we don't have access to this sector. These are the two states that we have available to us. And thankfully, that's exactly enough to define a single qubit. So I will define the 0, 1, 2, 0, 3, 4 state to be my logical 0. And I'll define the 1, 1, 2, 1, 3, 4 state to be my logical 1. All right, so next I'd like to ask what these braid operators do to those qubit states to see what braiding allows me to accomplish. All right, so let's start by, well, actually just maybe one bit of bad notation. Please don't confuse that 0 and 1 for what I defined as 0 and 1 in the Kitaev chain context. Hope there's no confusion. These are the logical qubit states I think I previously called 0 and 1. The opposite fermion parity states in a single Kitaev chain, but this is not the same thing. All right, so let's start by, basically what I want to do, I just want to take these braid operators and ask how they transform our logical 0 and 1 qubit states. All right, so let's start with 0, 1, 2 acting on the logical 0 state. So this would correspond to some adiabatic braid of Majorana 0 modes gamma 1 and gamma 2. This actually has exactly the same effect as what I would get by swapping gamma 3 and gamma 4 because the occupation numbers are exactly the same. Right, so let's just look at the U12. All right, so for U12, I'm going to have a factor of I gamma 1, gamma 2 sitting here. Now, the occupation number 0 state for that 1,2 fermion corresponds to a state where I gamma 1, gamma 2 is equal to -1. Is that okay for everybody? Usual occupation number relation. And so this is just going to enact a phase on that state corresponding to e to the I pi over 4 times -1. Suppose now that I did the same set of operations, either U12 or U34 on the logical 0 state. Again, it doesn't matter whether you enact braid gamma 1 and gamma 2 or gamma 3 and gamma 4. The effect will be the same. Right, and the only difference is that in the logical 1 state, these d fermions are occupied. Correspondingly, the I gamma 1, gamma 2 flips from -1 to +1. And instead of getting a e to the minus I pi over 4 phase, we'll just get a e to the plus pi I over 4 phase. All right, so this is already interesting. We haven't actually rotated our quantum states based on this particular operation and based on those particular starting states. But there is something interesting because we basically generated a phase gate on a qubit. There's a question?
Yeah, probably a stupid question, but why was the total fermion parity conserved again?
God says so. A more illuminating answer, I suppose, is locality. So you can ask, what would it take for me to break fermion parity conservation? So I could be perverse and I could say, well, okay, let me try to add to my Hamiltonian some operator like Cx plus Cx dagger just to make it Hermitian. So you might say, well, why can't I just add that? So that will clearly break fermion parity conservation. But you'll run into all sorts of issues with locality. This thing is not local by virtue of fermion anti-commutation relations. And you can set up thought experiments, something like measure the energy density of your system infinitely far away from this position x, and then, maybe I'm flipping it. I think if you measure the energy density at this position, then add a fermion infinitely far away, and then measure the energy density again, you'll find that it's not the same, and that's bad.
But how does the for Majorana system decide in which parity it lives then? Vidya or whoever is making the device decides. I mean, they have some number of electrons in the device, and maybe what you're asking is, how did I know that this set of states had even fermion? Why did I say that these were even fermion parity versus those? That's arbitrary too. Actually, that's a convention that I chose. And that's has to do with there's some amount of arbitrariness in how I even define those fermions. Thanks.
Sure. All right. So maybe nothing too striking, but it is kind of interesting that we can at least get a phase gate from a swap. What's much more interesting in this context is what happens if we swap gamma 2 and gamma 3. Okay. So let's look at that one. Let's look at what happens when we act U23 on the 0 qubit state. All right, so here at least as far as I know, I have to use this cosine plus I sine formulation of that U23 operator. So let's write it explicitly as cosine pi over 4 plus I gamma 2 gamma 3 times I sine pi over 4, acting on 0. And so here's where things get a little bit
a little tricky. So, this state is simply expressed in terms of occupation numbers of D12 and D34. But now this is a mixture of gamma 2 and gamma 3, and those will not have a simple action on the state 0. And I think the best way to proceed is just to recast this I gamma 2 and gamma 3 combination in terms of the operators that we know how they act simply on that state. So let's just take this I gamma 2, gamma 3 and use these equations to rewrite them slightly. So to get I gamma 2, that's just D12 minus D12 dagger. And the gamma 3, that's just the real part of D34, so that's D34 plus D34 dagger. And fortunately, this looks kind of awful, but the annihilation operators we can just drop because they're acting on the state for which those fermions are absent. So let's just kill those. And what we end up getting is, all right, so from the cosine pi over 4, we're just going to, there's some component that will remain in the same state, the same 0 state. And let me just use square root of 2's now. But from the D12 dagger, D34 dagger, so those act non-trivially on the state 0 and will produce the logical 1 state. And so let me just define D12 dagger, D34 dagger to be 1. So then we have a minus sign and an I that we need to cart around. So this is minus I times 1. Okay, so much more impressive thing. We started in one ground state. We performed some adiabatic swap of Majorana 0 modes, and we went to a physically distinct ground state. So similarly, if you look at U23 acting on 1, this will produce 1 over the square root of 2 times 1 minus I 0. Okay, so this is a different kind of qubit operation that we have access to now compared to the phase gate. So this actually introduces a non-trivial rotation on the Bloch sphere. So if the, let's say, 0 state is the southern pole, the 1 state is the north pole. If you were to start, let's say, at the south pole in the 0 state, you perform a swap, then you make your way to the equator. Okay, so this enacts a pi over 2 rotation on the Bloch sphere. Let me comment on something that Charlie Marcus mentioned in his talk yesterday. I think in response to a question that somebody asked, how do you detect non-abelian statistics, which I think is that requires many levels of answer. But let me just phrase that in terms of a concrete protocol. Let's assume that you can perform measurement and readout in these operations. Here's, I think, a dream experiment, at least for me. So let's suppose that you have this qubit. You perform a swap of, you're able to perform a swap of gamma 3. Let's suppose you initialize your system into the 0 qubit state. You perform that swap, and you end up on the equator. If you then measure, what the state of your qubit is, you'll find that it's completely fuzzy. So half the time you'll find that you get the 0 qubit state, and half the time you get to the 1 qubit state. So it becomes a maximally random readout. And so if you were doing this experiment and you started with some well-defined initial state, and you performed some operation, and you got a random answer, you should be very excited, but obviously very cautious as well, because randomness, how do you know that you just didn't muck up your system so badly that there were noise and God knows what else happened to just randomize the state of your qubit. So you can, I think, pretty sharply rule out such a boring scenario, you can process your qubit even further. So start once again from the 0 qubit state, perform not 1 but 2 sequential swaps of gamma 2 and gamma 3. So that pi over 2 rotation then becomes a pi rotation on the Bloch sphere, and should flip you from the 0 state to the 1 state. Now when you perform a readout, you should get a deterministic answer, assuming all goes well. Every time you do this double braid procedure, you should
find that you flipped your qubit state. And I would, to the extent that you can possibly do this, I don't know if Charlie Marcus is here, but maybe he would maybe not even object to me using the word prove in this case. I think if you saw that, how else could that arise? I think it would almost require some kind of divine intervention for randomness from one braid to arise from noise, but you do even more to the system and you somehow get a deterministic answer back. Okay, so one final feature I should emphasize about these operations is that nowhere have I told you exactly what path or by what mechanism these zero modes have been swapped. This information is quite rigid. The information encoded in this unitary operator is rigid. It does not depend on those non-universal details. The only thing that matters is something topological. Which Majoranas did you swap, and in what order? And so, correspondingly, the dream is that at least this restricted set of gates that you have access to are kind of inherently fault tolerant to noise and have a lot of resilience to whatever uncontrolled things might be going on in an experiment. All right, how much time do I have? Who's the chair, actually? Okay, sounds good. Should I stop? Okay. All right, so, there's many natural questions, I suppose, that people can ask at this point, but maybe one, so I've kind of laid out what you might like to do. You want to make topological superconductors. You want to figure out how to braid them, demonstrate non-Abelian statistics, enact these topologically protected qubit operations. But how do you actually, let's back up all the way to step one. How do you know that you've actually made a topological phase in the first place that has Majorana zero modes? I think that's the only thing I'm going to have time to wrestle with in my remaining time. There's a secondary question, though, you could ask, which is, suppose you do an experiment and you're sufficiently confident that you actually have a device that harbors Majorana zero modes. How do you actually read out the quantum information that they encode so that you can actually perform these kind of higher level probes of non-Abelian statistics, fusion, and so on? I'll have notes where we can discuss offline that second question of readout, quantum state readout. But for now, let me just say a little bit about, yeah?
So super basic question. So how do I see that T1 on the student is, so is this supposed to be like super large? Is it obvious? Or?
Well, I think it, yeah, so T1 will ultimately be, so I guess you're asking, suppose I initialize my system into 1, and then, maybe it wants to be in 0, and then over what time scale can it relax?
Okay, but for the reasons you mentioned, I expect T2 to be large, but do I expect also T1 to be large?
Yeah. Okay, that's a good question. So let me say something about that. All right, so ideally, you will have Majorana zero modes, which are, macroscopic distances apart from one another. And, so imagine this is, these are a mile away. So you can ask, suppose I start in the 1-1 state, how can I get to the 0-0 state? And basically, that would require you to kind of move a fermion that's kind of non-locally embedded in this state and transfer it over to this other thing, which could be arbitrarily far away. And so, in an ideal world, that is going to take a very, very long time to happen because there's, a gapped medium that intervenes in between these widely separated Majorana zero modes.
So, okay, so if I have like implemented two monotypes, then they have to be like far from each other?
Yeah, I mean, far is a relative thing, but you should not have, so you don't want to have any transfer of fermions between adjacent Majorana zero modes. So actually, I would say that in the ideal theory world that I live in, the same property that protects dephasing errors also protects relaxation errors. But would be remiss to not say that there is a different world from the one that I live in, which is the real world, the experimental world that people have to confront if they want to build this. And there are detrimental processes called quasi-particle poisoning, which can, basically straight even if this medium is fully gapped everywhere and you just have isolated zero energy degrees of freedom, that does not necessarily mean that that gapped region is always in its ground state. You can have stray quasi-particles that roam around, and that can, if you have some quasi-particle that can relax into one of these zero modes, that can not only produce bit flip errors, but perhaps even more unpleasantly can introduce can mix in this non-computational subspace. Yeah, a very good question. Okay, so I'm not entirely sure that I'll be able to finish this next thing in whatever time I have left, but let me just try to get as far as I can. By far the most popular method of trying to probe the existence of Majorana zero modes and therefore ascertain evidence that you have a topological superconducting phase relies on electrical transport, so namely tunneling measurements that take a lead and then try to tunnel electrons from that lead onto the position where you hope some Majorana zero modes are sitting. So I wanted to give some theoretical perspective on that kind of experimental setup. So let's suppose that you have some topological superconductor that has Majorana zero modes, which I'm going to call gamma and gamma prime. Doesn't matter whether this is 1D or 2D topological superconductor. I'm going to assume that except for the Majorana zero modes, I'll assume that that superconductor is gapped. We'll connect it to ground. And then I'd like to take a spinless lead. And I'm making it spinless just for simplicity. Problem just easier to deal with, but the qualitative conclusions won't change. Okay, that spinless lead is going to be held at bias voltage V relative to that grounded superconductor. And we're going to allow the electrons at the end of that spinless lead to hybridize with the Majorana zero mode with some amplitude T. All right, so what I'll specifically be interested in is the conductance that describes current flow to ground, so the dIdV conductance, in the limit where temperature is 0, because I'm a theorist and that's where things get more universal and more simple, and also in the limit where the bias voltage is small compared to the bulk gap protecting that superconductor. Right. One other simplification I'm going to make is that, it's not simplification, it's a perspective on the spinless lead that'll be very useful for analyzing the problem theoretically, is I'd like to imagine that the incoming and outgoing electronic states in that lead are actually described by a single chiral fermion that just kind of gets bent around on itself. Okay, so let's say that the edge of the lead corresponds to position x equals 0. The incoming states for this chiral fermion are at negative values of x, so x goes to minus infinity, is where the electrons come from. And then the outgoing electrons correspond to positive x values, and it's just a convenient coordinate system. Okay? So rather than having to keep track of right and left movers, I just can keep track of a single chiral fermion. Are people okay with this? All right. Okay, so I really like this kind of problem actually, because it's all the painful exercises we go through in scattering theory and in introductory quantum mechanics, where you deal with reflection and transmission coefficients. You see that that's actually useful for something like this experiment. And so let's imagine that we're an electron that's incoming from the lead, trying to make its way towards the superconductor. You can ask, what fate can I experience upon meeting that gap superconductor? And so, one process that we can automatically rule out is the possibility that that I can just jump into the superconductor and then make my way to ground. That's blocked by the fact that I'm tunneling at energies below the bulk gap for that superconductor. Okay, so that's, transmission processes are forbidden. Now, one thing that can, of course, always happen, independent of what kind of gap system you're looking at here, is that if you come in as an electron, you can just bounce back as an electron. So that would be an ordinary reflection process that wouldn't contribute to the current because no charge was emitted into the superconductor and therefore wouldn't contribute to the conductance. All right? If you were dealing with an insulator, that's the end of the story. But superconductors allow for a more interesting possibility because there's a Cooper pair condensate that's present here. All right, so there's a new process called Andreev reflection. So I can come as an electron. I can bounce back when I hit the superconductor not as an electron, but rather as a hole. In the process, to conserve charge, I deposit a Cooper pair into the superconductor. And since that's a Cooper pair condensate, that Cooper pair has no trouble contributing to the current and making its way to ground. All right, so that's the only non-trivial process that's available to me in the limit that I've specified that actually contributes to the conductance. And correspondingly, the conductance as a function of bias voltage has a very nice form. In the so-called Landau-Bodecker framework, there's an E squared over H conductance quantum times twice the probability that an incoming electron undergoes Andreev reflection, so the AR stands for Andreev reflection. That probability is going to be energy dependent in general, and the energy in which we should evaluate it is the bias energy. Right? Now there's a factor of 2 here, which reflects the fact that every electron that undergoes an Andreev reflection process deposits not 1 but 2 electrons into the superconductor, and that's why you get a larger conductance than you would compared to if you just were transmitting electrons one at a time into the superconductor. Okay, so that's what I'd like to figure out within some very minimal theoretical model. And I'm quite sure I'm not going to have time to get through this whole thing. And so I'll probably skip a lot and cut to the most interesting part. So first let me write down a Hamiltonian that describes this setup. It'll consist of 2 pieces, a part describing the kinetic energy in the lead and a part that represents tunneling onto that Majorana zero mode. Because of how I've modeled the lead as a chiral fermion that just kind of gets bent around, the lead kinetic energy is just going to look like the kinetic energy for a single chiral fermion. And for the Majorana hybridization term, there's going to be some energy scale T times gamma times psi. This lead fermion field evaluated at x equals 0, which is a location at which the lead comes in contact with that zero mode. All right, so that's I can write down a term that involves gamma coupling to psi, but that's not Hermitian, so I need to actually subtract from that psi dagger of x equals 0. And so that combination is our Hermitian operator that describes interaction between the lead and the Majorana zero mode. All right, so that's a theory that I'd like to understand. So if you wanted to solve this in a very satisfying way, you would open up your quantum mechanics, intro quantum mechanics book. You would find the wave functions describing the lead coupled to the zero mode. Those wave functions will be impacted to some degree by this coupling T. Exactly how that wave function is influenced will depend heavily on what energy, what kind of energy you're looking at. And by looking at the structure of those wave functions, you can just read off the probability that you have Andreev reflection. Okay. All right, so I think I'm probably maybe already out of time, so I think I'm just going to, well, okay, so let me try to just sketch in words. So there's 2 limits in which I'd like to think about this problem. One is kind of establishing a baseline. So let's suppose you're considering a bias voltage which is large compared to some characteristic energy associated with T, but still below the bulk gap. Okay? If that's the case, then you can think about T as a perturbation, and at 0th order perturbation theory, you can just ignore this line entirely. All right? If you ignore that line entirely, this problem is trivial to solve. You'll just get plane wave eigenstates for this chiral fermion. And there's no question that those eigenstates will just describe processes where an electron comes in and then reflects as an electron. Okay? And that limit of the problem, this Andreev reflection probability is just going to be 0. Okay, very uninteresting limit. You can, of course, do perturbation theory if you like in this T, and you'll get some residual corrections away from 0, but that's maybe a useful starting point. Another useful extreme to look at is the opposite limit, where you're tunneling at arbitrarily low bias energies. Okay? If you're tunneling at arbitrarily low bias energies, then the way to satisfy that constraint at the kinetic energy level is that you have just an incoming electron that has basically no momentum and no energy. Right? Now the question is, in the presence of this T term, which now looks large compared to your electron that's coming in with arbitrary low energies, how do you possibly get an eigenstate of this full Hamiltonian, including this HT term, when you're insisting that the energy is basically 0? Right? So we know how to get energy 0 from this piece. You just have the momentum for incident electrons being arbitrarily low. But how do you actually recover a 0 energy eigenstate in the presence of this T term? Okay. You can stare at this, and there's very little flexibility that you have for making sure that that's the case. Essentially, the only way for that to be possible is if psi acting on your eigenstate and psi dagger acting on your eigenstate exactly balance each other so that these things cancel and give you 0. Right? So you can think about this T term as basically imposing a new kind of boundary condition on your lead that's going to impose that psi is equal to psi dagger at x equals 0. Okay? So that's a boundary condition that's kind of dynamically generated by the coupling to the Majorana 0 mode when you tunnel in at very low energies. Okay, so we can guess the form of a wave function, of an incoming electron wave function that has that property. So let me just sketch what the probability weight would look like. Right, so this is going to be as a function of x. Here's x equals 0. This is where my lead hits the Majorana 0 mode. All right, so this is going to be some psi squared kind of metric. So remember, we have both electron and hole parts to the wave function. We should allow for the possibility that we have Andreev reflection. For negative x's, those correspond to my incoming states according to my coordinate system. And so I'm going to assume that we just have some purely electron-like component to the wave function in that region. But if I want to satisfy this boundary condition, then this had better die. And in its place, we had better revive a whole part of the wave function. Okay, and you can see that right where those things cross, psi and psi dagger, it's going to have equal electron and hole contributions, and so this boundary condition will be satisfied. Right, so this kind of wave function describes a very different situation from what we had at high energies. This wave function describes a process where, with unit probability, I come in with an electron and I bounce back as a hole, depositing a Cooper pair into the superconductor. In other words, at low bias voltages, this Andreev reflection probability becomes 1, and you get a conductance, zero bias conductance, which is quantized at 2e squared over h. Right, so this is the zero bias peak, which provides a very nice consistency check with the existence of Majorana 0 modes. Here's where you have to be very, very careful using anything that's close to the word proof, as I think Charlie Marcus really hopefully drilled home in his lecture yesterday. There are other sources of zero bias peaks, and I think the most worrisome thing in most experiments is that it may be very difficult to distinguish based on a measurement of this type, a situation where you have a nice topological phase with Majorana 0 modes separated by large distances from each other, from something that's trivial but happens to have a little small bubble of not really meaningful topological phase, but a pair of modestly separated Majorana 0 modes, only one of which your lead actually sees appreciably. And so that's a quite tricky thing. And so nowadays people appreciate this issue, and there's a lot of emphasis on adding new kinds of measurement diagnostics, looking at tunneling from both ends of the device, searching for topological phase transition, and so on to try to get to more decisive signatures of Majorana zero modes. You have a question?
So if you didn't have a then you can't get this unbraid process?
You certainly can, sadly.
If you have a superconductor anomaly, low Majorana zero modes, and you can get this unbraid process, except it won't be sharply frequency.
Okay, yeah, so good question. So one thing I should emphasize about this result is it's completely universal, actually. Oh, yeah, so the question is, how could you get this sort of thing in a situation where you don't have Majorana zero modes, if I understand, and to what extent could you potentially confuse, let's say, a quantized zero bias peak from Majorana zero modes with something else that has nothing to do with Majorana zero modes? So this result is really universal. I've written on a very simple Hamiltonian, but you can add all sorts of other terms if you like, and it's unavoidable that in the limit of zero bias tunneling, PAR goes to 1. And this boundary condition is a very resilient thing. Now, if you, let's say, had a non-topological superconductor, even without, let's say, zero energy, suppose I add spin, because that is actually important for getting Andreev processes at low energies in non-topological superconductors. You can get, with a spin-full lead, you can get, actually the zero bias conductance is non-universal, at least within some treatment of this type. And you can get anything from 0 to 4 e squared over h. And it could be that maybe the system happens to have a conductance which is close to 2 e squared over h. It could be accidental, the result of fine-tuning, maybe the result of hunting around in parameter space. But there is a more, I think phrasing things in that way kind of hides a bigger problem, which is that there may be generic reasons why it's easy to get some situation like this, where you have most of your devices is trivial and you have a little narrow segment that's kind of almost topological if you can just make it bigger. This situation can arise pretty generically from, it may also require some fine tuning, but if you have the luxury of tuning gates and so on, it may be hard to, you may think that you've landed in a topological phase, which also requires tuning to some degree, but in fact you've just gotten something like this. So this is the kind of thing that I think is a big worry in the field. All right, so I think I'm probably badly over time, and I apologize for that. I'll just maybe say one closing remark. I think hopefully I've shown you some opportunities that are unfulfilled in realizing the first topological qubit, and I think there's all sorts of amazing opportunities for discovery and new ideas to try to make that milestone eventually happen. And hopefully some of you will be interested in providing new ideas and trying to work towards that dream. So thanks for all the great questions. I really appreciate it.